An object's change in velocity equals acceleration versus acceleration times time. So this would be another way of rearranging that initial equation that we had. So remember, initially we had acceleration is change in velocity over change in time. Well, if I rearrange that equation for change in velocity, it's going to be equal to acceleration times change in time. Okay? So here's an example. A car having an initial velocity of 10 meters per second accelerates at 5 meters per second squared. After 1 second, its speed is 15 meters per second. After 2 seconds, its speed is going to be 20 meters per second, and so on and so on. So how did they get that? They got it based on this equation, okay? Where we're just rearranging. So here's our initial equation for acceleration, and we're just rearranging it, okay? And we get change in velocity is equal to acceleration times change in time. Well, what is change in velocity? What does that little delta sign mean? The little triangle. What does the triangle mean? Which means we do what? Mathematically, what does it mean? We subtract final minus initial. So I could rewrite this as VF minus VI equals A delta T, okay? And if I wanted to find the final velocity, what would I need to do? How would I get VF by itself? If I wanted to take this right here and find VF, how would I do that algebraically? I would add VI to both sides, which is how they get that equation. Okay, so this might be another equation you want to jot down. All of the equations that we have in this chapter are going to be derived from or come from this initial equation up here. Okay, so if you want to memorize all the equations, okay. If you want to derive them, that's okay too. Okay, but to me, it'd be easier just to memorize them. But whatever works for you, however your brain works and remembers things is fine. But this is where this equation comes from. V final equals V initial plus the acceleration times the time. So you can find the final velocity of any object if you know its initial velocity, its acceleration, and its time. And using that equation is how our example got those answers.
I'm sorry, this may be a dumb question.
Nope.
I've got make
not a dumb question.
Stuff just right over my head. So when it just comes down to the AT, that's assuming you've already done the final minus initial for the time, correct? Because you dropped
yes. Okay. And if you look at our example, it would be that you're at 1 second. So our time is 1 second. So let's plug into this and see. So if our car has an initial velocity of 10 meters per second, I would put in 10 meters per second for VI. Our acceleration is 5 meters per second squared. And they want to know what's the final velocity after 1 second. Okay, so if we did the final minus initial, that would be 1 minus 0, which is just 1, right? Okay, so my seconds cancel there, and I have 10 meters per second plus 5 meters per second, which is 15 meters per second. Okay? Does that make sense?
Yes.
Okay, then if we did it after 2 seconds, we would do the same thing. We would say, all right, I got my same initial velocity, 10 meters per second. My acceleration is 5 meters per second squared. But now my time is 2 minus 0. 0 being my initial time. Okay? And 2 seconds later is where I want to know what my final velocity is. So again, my seconds cancel. That's going to be 10 meters per second plus 5 times 2, which is 10 meters per second. And that gives me 20 meters per second. Okay? So yes, the t there is assuming you've done final minus initial. And almost all the time, your initial time is going to be 0, which is why we don't really subtract it out. Doesn't have to be 0, but most of the time it is. All right. Okay, so like I said, we love our graphs. So let's look at this graph of the velocity equation that we just learned about. Should look vaguely familiar. Maybe it'll look more familiar if I write this. Does anyone see any similarities between those two things? Yeah, it's pretty much the equation of a straight line, okay? Where A is going to be my slope, T is going to be my X, and VI is going to be my Y-intercept, okay? So when we have velocity versus time, the slope of that line is always acceleration, and the equation that you have there is the equation of a straight line. Okay? So the line is going to cross the velocity axis at a value equal to the initial velocity. So like I said, that's going to be our y-intercept. And the slope is equal to the acceleration. So if you want to make a graph of this, I would. And I would also make the correlation between the equation of a line. So, and this is only for velocity versus time graphs. So remember we had position versus time in the last chapter. Now we got velocity versus time in this chapter. For velocity versus time, the graph of velocity versus time, the slope is always acceleration. We're going to get back into those position versus time graphs a little bit later on, I think in 3.3. But for right now, everything we deal with is velocity versus time. Okay, we good? So when the acceleration is constant, so you are accelerating at the same rate all the time, so 2 meters per second every single second, that's when we'd say acceleration was constant. The average velocity, so when acceleration is constant, the average velocity is the sum of the initial and final velocities divided by 2. Now that's only when acceleration is constant. So when the slope of this line, remember, is acceleration. So when the slope of that line is constant, then we can say that the average velocity is final plus initial divided by 2. Just take the average. How much further do I want to go? So another way of writing that, and this is how it's actually written in your book, is you can write it as V average is equal to 1/2 times VF plus VI. or the other way around, doesn't really matter. Okay, so this is that statement. These two are the same thing. Okay, so I can add them together and multiply by a half, or add them together and divide by 2, and that's how we can get the average velocity when acceleration is constant, when it is not changing. Okay, I think I'm going to derive these two equations, show you where these two equations come from, and then we will call it a day, and I'll let you work on practice problems. We'll work on some practice problems for the rest of the time. So this would be, like I said, all these equations are just looking at different situations and what you have in a problem and how you can use what you have to get what they're asking for. So remember we talked about position versus time. We got this equation last chapter, that the final position is equal to your initial position plus your velocity times your time. If we apply that situation where velocity is changing, where your velocity is not constant, then we replace the V with V average. Okay, so I replaced V with V average, and that gets me this equation. I can find my final position, and that's going to be equal to my initial starting position times my average velocity times the time. And then they're going to do one last thing. They're going to take what average velocity is equal to, and they're going to plug in for average velocity. And when they do that, they're going to get this final equation down here. So expressing the average velocity in terms of initial and final gives us the equation to find, and this is what you want to write down, this is how you would find position of an accelerating object. You want to find the final position of an object that is accelerating. You're going to need to take its average velocity times its time and add that to its initial position. But you should begin to see kind of a pattern and some similarities. They're kind of based on the same equation. We're just deriving and substituting in to come up with a new equation that works for our particular needs. Okay? So there's some that are like set all the time, like the acceleration is always change in velocity over change in time. This one for final position is the same all the time. But we may make a little tweak here and there on it to account for different circumstances. So like I can find final position in a circumstance where my object is accelerating. It's the same general equation. I just derived it, substituted in another equation in place of what I was looking for. Okay? And that's what we do all the time. We just combine 2 or 3 equations and substitute in and come up with something that we need. Okay? And the reason we can't just use this equation is because if my object is accelerating, it does not have constant velocity. So I can't just put in one velocity because I don't have a constant velocity if I'm accelerating. But I do have an average velocity. Okay, so I can use that. All right. That was our one equation. Let's see what the other one was. So here's an example. Yeah, here's an example, and then you'll have the rest of the time to do your work. The equation for determining the position of an accelerating object may be used to find the position of a boat having an initial velocity of 1.5 meters per second, accelerates with a constant acceleration of 2.4 meters per second squared for 5 seconds. So we are looking for, so when you're reading these problems, you got to figure out what am I looking for and what do I have. We want to determine the position of an accelerating object may be used to find the position of that boat having initial acceleration. So velocity time equation for constant acceleration is right here. So I can find the final velocity if I know the initial velocity, the acceleration, and the time. And that's what I was given: initial velocity, acceleration, and time. So I've got my kind of list of equations over here. I have my list of things I'm given in that problem. Which one matches up? Which one has initial velocity, acceleration, and time in it? VF equals VI plus AT. And after that, it's just kind of plug and chug. Make sure you put your units in because your units do have to be consistent. So you have to make sure your seconds cancel with your seconds squared. And I'm telling you, especially on a test, they're going to try and trip you up because instead of saying 5 seconds, they're going to say 5 minutes. And what are you going to have to do? Convert minutes to seconds first. Okay? You're going to have to convert minutes to seconds first and then put into that equation. Yes?
Okay, so like in this question, what's the wording that like indicates that I need to find the final velocity? Because it says determining.
Yeah, I know. I was looking at that too. Determining the equation for determining the position of someone may be used to find the position of the boat. Yeah, that's crappy wording.
So normally it'll tell you.
Yeah. Yeah, after rereading that, going back and reading that the second time, I was thinking, they worded that really weird. So, yeah, that's not good wording. It should have said something about determine the final velocity of the object that is accelerating or has constant acceleration of 2.4 meters per second squared with an initial velocity of 1.5 meters per second for 5 seconds.
So the statement of determining the position, is that just telling you what?
I think that should be telling you what you needed to do, but it didn't. It should have said velocity instead of position. I think they messed up on that one. Oh, or I didn't turn the slide over one, and this is a whole nother half of the problem. Okay, so we're trying to find position. So if this was the end of the problem, yes, they should have said determine the final velocity. Okay? Unfortunately, this isn't the end of the problem. That was just part of it. Okay. So we still are trying to find position, which is X final, XF, right? So in order to find that, we ultimately are going to use this equation. Because that's our equation for position. XF equals XI plus 1/2 VI plus VF times T. All of this right here is our average velocity, which we had to use that first equation because they didn't tell us what the final velocity was. They told us what the initial velocity was. So that's why we had to use that first equation there on the previous slide. We had to use this equation to find out what VF was. So this is a 2-step problem, a 2-equation problem. We have to find final velocity before we can put into our position equation to find the final position. So that's why it was not making much sense. I didn't turn the slide over. So our initial position, remember, is 0 because that's our starting point. We are given the initial velocity. We found the final velocity. Our time is 5 seconds. And then we're just plugging and chugging and getting the answer. Okay. All right. Yeah, that's where we're going to stop. So let's do the practice problems. Let's do the practice problems for 3.1, which is going to start on page 76 and go all the way through to page 81. So that should be 1 through 18. We'll leave off the challenge problems, so 1 through 18. So let's look at number 2 together. The winner of the drag race, shown in figure 3.3, was traveling with a speed of 140.3 meters per second at the end of the quarter-mile course. The car started from rest and have an average acceleration of 30.4 meters per second squared. What was the winning time for the race? All right, so let's make a list of what we have. We know his speed, or his velocity, is 140.3 meters per second. That's at the end, so that's going to be his final velocity. The car started from rest, so his initial velocity is 0. And his acceleration is 30.4 meters per second squared. And what are we looking for? Time. So we need an equation that is going to relate final velocity, initial velocity, and time. And that is our average acceleration equation. Remember, it's change in v over change in t.
What are we finding?
We're finding time.
Oh, okay.
We know acceleration, that's 30.4 meters per second squared. We know final velocity is 140.3 minus 0. And we know the time is what we're looking for. Yes, ma'am.
Can I get a bathroom?
Yes, ma'am. So I'm going to multiply both sides by t. And then I'm going to divide by 30.4. If I do that, meters cancels with meters. One of these seconds cancels with one of these, leaving me a seconds, the unit of seconds, which is what I need because that's time, right? So my units have canceled out, and that's going to help me know that I've picked the right equation. So 140.3 divided by 30.4 comes out to be how much? And how many significant figures should my answer have?
4.6.
How many significant figures should it have?
Oh, okay. 4.61.
Let's round that. What comes after the 1? Yeah, so we'd round up to 2. So 4.62.